In this video, we'll deal with the heating effect on sulfates. Now let us have an idea what should be the general decomposition product of any sulfate compound, and for this let us start with H2SO4. So when H2SO4 is heated, then we get the oxide of hydrogen plus SO3 molecule, and on heating SO3 molecule above 800 degrees Celsius we get SO2 plus O2. And just for the information, SO3 can be of alpha, beta or gamma types, alpha and beta are polymeric chain structures and gamma are cyclic structures. So let's come back to the heating effect of sulfate. So on the basis of the above case of H2SO4, if we compare it with the metal sulfate, then we will find that when metal sulfate is heated, then we get the oxide of that particular metal plus SO3, and now when this SO3 is heated above 800 degrees Celsius, then we would get SO2 plus O2. Now this heating effect on sulfate is going to be a little tricky because we won't always see this particular decomposition trend. We will see some deviations from it in some specific cases, and just to make things easy, I will try to explain so that you could remember when we would see such deviations. So let's start with some examples here. We have Fe2SO4 whole thrice. This we have to heat. Now from this compound we can infer that Fe must be in +3 state. So when this happens and when we heat below 800 degrees Celsius, then we get the oxide of iron Fe2O3 plus SO3, and when we heat it above 800 degrees Celsius, then this particular SO2 would break down into SO2 plus O2. Similarly, the case with Cr2SO4 whole thrice, below 800 degrees Celsius we will get SO3 apart from the oxide of chromium, and above 800 degrees Celsius this SO3 will decompose into SO2 plus O2. Now ZnSO4.7H2, it is also called white vitriol. So when it is heated, it will first lose its water of crystallization and it form ZnSO4. Next, below 800 degrees Celsius, oxide of zinc plus SO3, above 800 degrees Celsius, oxide of zinc and SO2 plus O2. So here comes the exception that I was talking about when we are discussing the general decomposition product of any sulfate. So when the sulfate of chromium, where chromium is in +2 state, is heated below 800 degrees Celsius, then we get the oxide of chromium, where chromium is in +3 state, plus SO3 plus SO2. So generally we should have seen in the product only SO3, not SO2, but here in the case of chromium, in the case of chromium sulfate, where chromium is in +2 state, we see SO2 additionally. So the proposed reasoning that can be given is that here we see that chromium has oxidized from the +2 state to +3 state, and the SO3, in the SO3 we see that sulfur has +6 oxidation state, and in the CrSO4 also the sulfur has +6 oxidation state. So we can see that chromium has oxidized from +2 to +3 oxidation state. So something must be reduced in order to have the redox reaction. So here we have sulfur in +2 oxidation state as well as sulfur in +4 oxidation state. So we can see that chromium has oxidized from +2 to +3, and at the same time sulfate has reduced from +4 to +6 to +4 oxidation state. So just to remember it, just to have a hint when we are solving such type of questions, we can understand these kind of exceptions in this way. And now above 800 degrees Celsius, it is simply that SO3 has broken down into SO2 plus O2. So in the final product we are getting Cr2O3 from this step and SO2 from this step and SO2 plus O2 from the decomposition of SO3. So you can write 2 molecules of SO2 as well. Now in the sixth case also we have some exceptions, where SnSO4, where Sn is in +2 state, it's heated below 800 degrees Celsius and we are getting SnO2 plus SO2. We see that Sn has oxidized from +2 to +4 state and sulfur has reduced from +6 to +4 oxidation state, and above 800 degrees Celsius also we see no change in the decomposition product because sulfur is already in SO2 state when it is heated just below 800 degrees Celsius. So just I have tried to give some explanation so that you can remember when you are solving the heating effect of these compounds. Next, FeSO4.7H2, it is also called green vitriol. So when it is heated, then we will first remove the water of crystallization, that is 7H2O, would be removed and we'll get FeSO4. Now when FeSO4 would be heated below 800 degrees Celsius, we would get the oxide of iron plus SO3 plus SO2. Here we also see that iron is in +2 oxidation state. Similar explanation can be given as we have discussed in the case of CrSO4 for such kind of decomposition product, and above 800 degrees Celsius this SO3 will break down into SO2 plus O2. Similar explanations for this too. And now let us do some more questions. In PbSO4, when it is heated below 800 degrees Celsius, we are getting the oxide of Pb plus SO3, and above 800 degrees Celsius we will get SO2 plus O2. Okay, it will come from SO3. Now in the second part we have to heat PbSO4 whole twice, where Pb is in +4 oxidation state and sulfur is in +6 oxidation state. So on heating this compound we will get PbO2, where Pb would still be in +4 oxidation state and sulfur would still be in +6 oxidation state. There is no change in oxidation state and this would be an intermediate product. And on further heating, PbO2 will get PbO plus O2, as was discussed in the lecture when on the introduction of heating effect, that PbO2 when heated will give PbO plus O2 and SO3 when heated will give SO2 plus O2. So the final product would be this PbO plus SO2 and plus O2, which is common in both the product. So the final product is here PbO plus SO2 plus O2. Now let us look into the decomposition product of CuSO4.5H2O, which is also called blue vitriol. So when we look into the structure of this blue vitriol, we find that the water of crystallization, that is 5H2O, is linked in such a way that all the waters do not get removed all at once when blue vitriol is heated. We see that two water molecules are having one linkage, these two water molecules are having two linkages, and this one water molecule is having 4 linkages. So when we heat blue vitriol, these two water molecules will get removed first, which are having one linkage, followed by these two water molecules which are having two linkages, and finally this one water molecule which is having one linkage. So this is the decomposition trend of CuSO4.5H2O, that is blue vitriol. So when blue vitriol is heated, in the first step, two water molecules which were having one linkages got removed and the resulting product was CuSO4.3H2O. On further heating, the next two water molecule which were having two linkages got removed and the resulting product was CuSO4.H2O. And the final step, the last water molecule, water of crystallization, which was having 4 linkages, got removed and the resulting product was CuSO4, that is dehydrated copper sulphate, which is white in color. On further heating CuSO4, the general decomposition trend would be followed, that is the oxide of copper plus sulfur trioxide SO3. On further heating, we get SO2 plus O2 from SO3 and Cu2O from CuO. Now this conversion of CuO to Cu2O, this has been discussed in the introduction video on heating effect. We see that the copper in +2 state got transferred into copper in +1 state on heating. Now finally the heating of gypsum. When gypsum is heated, gypsum is CuSO4.2H2O. When it is heated, then the resulting product is CuSO4.5H2O, which is also called plaster of Paris. On further heating CuSO4.5H2O, we get the dehydrated calcium sulphate, that is CaSO4. On further heating this calcium sulphate, we get CaO plus SO3. Now you can further heat it and you can get CaO plus SO2 plus O2. So now the thing to remember is that CaSO4 is called dead burnt plaster and CaSO4.5H2O is called plaster of Paris and CaSO4.2H2O is called gypsum. So this was it from the decomposition product of sulphates. So in next video we'll deal with the heating effect on ammonium salts.